Hey everyone, I'm Joe. I'm the creator of Luminal. Luminal is a new ML framework in Rust that I'm working on. I have been getting quite a few questions about using the framework, about why it's designed the way it is, because it's quite a bit different from other frameworks out there, and about my goals that I have for it in the future. And so I just figured I'd make this quick intro to sort of sum up um, a lot of those points in a nice, succinct way. So starting off, why did I decide to go make a new framework? There's a lot of great options out there already. Um, well, a lot of them are pretty similar out there. There's a lot of, it's sort of like the paradox of choice. There's a lot of great frameworks out there, but most of them work in a very similar way. And so there's the differences between them aren't too big. I kind of wanted to explore the possible design space of these frameworks. And then another reason was that primarily it's motivated by production use cases and specifically on-device inference. A lot of these frameworks are designed with research in mind, so they're in Python. They're designed for like hackability and ease of use, to experiment with different model architectures. But that wasn't really the use case I was interested in. I really care more about production grade sort of software running on device, and as efficient as possible. So existing landscape, I'll go over real quick, is like we have PyTorch and we have TensorFlow 2, and these are very similar frameworks now. They're both eager execution, dynamic. So what does that mean? Well, that means like when you have A plus B, when you actually see that in the code, the addition happens right then and there. So A data gets added to B data. If you're doing this on the GPU, it'll trigger an addition kernel. If you're doing it on the CPU, it'll just do a SIMD for loop or something like that. And so it's very straightforward to program, but it also is somewhat limiting, because your code is only as optimal as you write it. So it's up to you to write very optimal model code. And what is optimal on one hardware may not be optimal on another hardware. So you end up with like a very complex model code that sort of needs to like target different hardware and have like if else statements depending on what hardware it's running on. The other end of the spectrum would be something more like XLA, and JAX. JAX is essentially a layer on top of XLA. And TensorFlow 1 actually took this approach as well, where you basically you define a computation ahead of time. So you define your whole neural network, you send input tensors through it, and you would have, for instance, A plus B. So A plus B wouldn't actually happen when you see that written in the code. What it would do is it would just record that addition to some data structure, and then it can run all those operations later on, or it can compile them first and then run them later on. And so that gives you the added benefit of being sort of like a layer of abstraction above the hardware. And you can turn that, it turns out like you can do a lot with that layer of abstraction. As I was going through this, I figured like, okay, compilation is cool because we could do like stuff like kernel fusion and maybe get a little bit of a speed bump over PyTorch. And as I went through this, I sort of realized that a lot of these concepts that are first class citizens in these other frameworks, turns out you can codify them in fancy compilers. So you can codify data types, devices, you could likely do even training, all encapsulated in the compiler instead of in the core framework. And so what that means is the core framework ends up being dirt simple. And that's like one of the guiding philosophies behind Luminal. I actually took a lot of these inspirations from TinyGrad. So like the minimal line count for the core library is always a North Star. Like we should be dead simple. You should be able to go through the core library and understand it in an afternoon. And if you can't, we're too complex and we have to go back and refactor something. So simplicity will always be core, and we're able to get more simplicity than anyone else because we can offload a lot of complexity to compilers. Now, that doesn't mean that complexity doesn't exist, but it does mean that it's sort of moved and externalized and isolated into a compiler. So simplicity will always be good. Of course, none of this matters if you're still slow. So speed also is like a core principle that I went into this with. I don't want, like, there's not a big use case for slow ML frameworks. I don't think anybody wants to run slowly. So performance always will be a big priority as well. And then another really interesting thing that I liked, that I was inspired by TinyGrad with, is this RISC style architecture. So having a minimal primitive operation set. So right now there are 11 primitive operations. That'll probably be reduced to 8 or 9 in the near future. And that's good not only for simplicity of like reading the code. You don't need to understand a whole bunch of different prim ops. It's also really good for portability. So say you want to implement a new accelerator. You want to implement Luminal on a new accelerator. You have some quantum photonic thing, and you want to implement Luminal to run on it. Well, you can do that now because you only need to implement 11 primitive operations, and every network supported by Luminal is now supported on your accelerator. So having this RISC style architecture is very important. It's also very important for compilers because there's a very limited number of ops that they need to like pattern match against or expect in the graph. Whereas if you had like a PyTorch style primitive operation set, your compiler needs to deal with like maybe 250 or 300 possible operations. So this also makes writing compilers a lot simpler. And then of course, because we're in Rust, like we want to be native, we want to compile down to a single binary. If possible, if your app is in Rust, then we just statically link to your app, and then your app ends up being a single binary with the whole inference engine included. So that sort of cuts through a lot of the crazy abstractions and virtual environments and Docker containers and everything that all these hoops people jump through today to do deployments, which are kind of a mess. And then, of course, obviously we want to be correct, so we validate as much as possible. We always want to make our tests better and better and better. If you ever want more tests, or if you find something that doesn't work and isn't covered by the tests, feel free to submit a PR. I'll almost definitely accept it because more tests are always better. So yeah, I sort of went into the differences between PyTorch being fully dynamic, eager execution based, and XLA. TinyGrad sort of falls into the middle of that spectrum where they try to do both. They try to get the best of both worlds. They do essentially lazy execution. So you basically write all your model code, and none of it gets ran until you need it. So say you need it for a print statement or for control flow or something, you can easily get that data. And when you get that data, behind the scenes, it will compile a subgraph, and then it'll run that subgraph and it'll give you the data out. So, excuse me. And so you sort of get the best of both worlds. You get the debuggability and simplicity of PyTorch, and you in theory get the speed of ahead of time compilation like XLA has. In practice, I think it's a very complex thing to master because now you need to optimize your compilation times because they're part of your runtime. So I was more interested in optimizing for like the simple case of let's just compile everything ahead of time. We'll give the compilers the maximum amount of global knowledge possible so that they can do the most aggressive compilations. And so that's basically the approach we take. So I will pull up like a pretty straightforward, simple example of Luminal. Let me just go ahead and run this. Okay, so yeah, if we run this here, we get out B. all B is, so basically what we do, everything is based around this centralized graph concept. So the tensor data is stored in the graph, the computation is stored in the graph. It's all on the graph. And what we do is we end up specifying a model here. So all a model is a linear layer in this case. It's all statically type checked, so the shapes of tensors are built into the types. This is a brilliant idea pioneered by a great library called DFDX in Rust. So all of this is type checked at compile time, so it's impossible for you to feed a tensor into a linear layer where the shapes mismatch. And so here we're saying that the linear layer has an input size of 4 and an output size of 5. And then what we do is we go and we specify an A tensor, so this is the input tensor. It's a rank 1 tensor of size 4, so it's just a 4-dimensional vector. We set the data here, and then we actually feed that through the forward linear layer, and then we do dot retrieve. This tells the graph that we want to actually fetch this data after it's ran, so don't throw this data out once it's computed. So then we go and we do cx.execute debug, and then we print out the B data. And so up till here, none of the computation actually happens. There is no tensor computation. But what we do is we execute it here, and once that's done, B is realized. B has actual data, so we can call b.data to get it out. And then because we're calling execute debug, we could just call execute, but execute debug gives this nice little view here where we can see the actual ops that were ran. So we load the tensor, we load the weights. The tensor is A here, and we load the weight for the linear layer. And then we do a multiply and a sum reduce. Well, that's kind of odd because we just forward through a linear layer? Why are we doing multiply and sum reduce? Well, actually a linear layer is a matrix multiplication. That's all it is. But we don't actually have a matrix multiplication in our framework, in our primop. And so, like I said, we have a RISC style architecture. These are the only ops we actually have access to. So we do mapmols by just doing an element-wise multiply and then a sum reduce. And that's equivalent, if you move the data around correctly, that's equivalent to a matrix multiplication. And so we see that this was the order they ran in. This is the amount of time they all took. You see the element-wise multiplication took the longest, followed by the sum reduce. You get the total time here, and then here we can see the output. So it's very straightforward. The interesting part comes not here, because this is just straightforward. We're just defining computation and then running it. But because we define it before we run it, we define it entirely before we run it, we can then do compilation on it. So if I uncomment this is the metal compiler, and it's the metal compiler, and we're passing in FP16 as the data type that we want to use. And what we do is we call this cx.compile, and we pass in the compiler we want to use. And then after we compile, then we execute. So actually, before I do this, we can do cx.display, and we can see the graph. And let's see what it's actually doing. So it gives us this nice little graph visualization. It looks exactly as you'd expect. So we load the weight, we load the tensor, we do an element-wise multiply, and then we do a sum reduce. Very straightforward. Now, let's do the compilation, and let's see what happens. This graph will look a bit different now. So it looks a lot more complex, but we can basically ignore this node and that node and just focus on these. So what we do is we still have the weight load and the tensor load, right? But we actually, our compiler inserted copy to device ops. And so, we had originally the weight and the tensor on the CPU, but we want to do GPU computation in metal. So using the GPU in my laptop here. And so we have to copy that data over to the GPU. And then notice that we're not doing the element-wise mul and the sum reduce anymore. We're actually doing a proper mapmul. And so we have in this metal compiler, we have a pattern match that actually looks for the mapmul pattern so the mole and the sum reduce, and then it replaces it with a very efficient matrix multiplication operation that happens on the GPU. And so then at the end, once we do that, we copy from device, we copy back to the CPU so that we can then access the final data. But so what you see here is that, again, none of our actual model code has any knowledge of the GPU or metal or anything like that. The only metal thing that we're running is the metal compiler. And this completely handles converting it all to metal operations to run on the GPU. And in this case, it even does type conversions. So this all actually happens in half precision. So this matmul is done in FP16. And so you can get very, very fancy with these compilers here, because all a compiler actually is a function that takes in a mutable reference to the graph and it modifies the graph. So you can get very, very, very creative with that. You can do complex pattern matching, or you can just do one-to-one op conversions. So you can convert from CPU ops to GPU ops, whatever. Or you can get really fancy and do like dynamic kernel fusion, where you're like fusing together arbitrary combinations of operations and then writing custom kernels and then compiling them on the fly. We also do that in Metal. But all this is for giving you a much more optimal graph to run on your device, on whatever device you're running on. And so what does this actually end up getting us? Of course, for this example here, like, it took us half a millisecond, and now it's taking us a millisecond. Like, we did all this and we actually got slower. Well, it's because we're doing like a tiny computation. But on a properly large model, this form of compilation actually matters. And so let's see like a properly large model. Let's go to Mistral here. This is a 7 billion parameter model. And it's running locally on my M1 Pro. And so if we run it here, we define the graph, we compile the graph, and then we load the weights in and we process the prompt, and now we're generating tokens here. And so this is like running completely local, running at 15.3 tokens a second. I think the screen recording probably slows it down a little bit, but you can see like we can run pretty quickly here. We don't actually have like hand-tuned kernels just for Mistral like a lot of other projects do. Some projects, they really want to run Mistral or run LLMs really quickly, and so they have hand-tuned kernels that just do LLMs really fast. But of course, then you sacrifice the flexibility. You can't actually run other architectures. So we're able to achieve this speed in a very general purpose way. So all of the compilers used to get to this speed can also be used to speed up convolution networks, or whisper or diffusion networks, stuff like that. And so that's sort of like the guiding philosophy of like we can use these compilers to get really fast speed in a flexible manner, right? So of course we can get better than 15 tokens per second, but that's where we are today. So I went over compilers, I went over the philosophy behind that, and compile time shape checks and stuff like that. So where are we currently? We have Metal and CUDA backends supported. Metal is far and away the most fleshed out backend. That's where I've spent just most of my time. But CUDA is still pretty decent. It uses cuBLAS for matrix multiplication, which is pretty quick. We are within 20% of Llama CPP on M series Max, and Llama CPP is like a very well optimized, hand optimized library. So yeah, we have support for Mistral and Llama right now. Of course, I'm very biased towards LLMs, but we want to support more architectures. So if you want to implement Whisper or diffusion models or stuff like that, absolutely, by all means, submit a PR and we'll put it in the examples. We have like a neural network library. It's a fairly minimal neural network library, and I'd like to keep it fairly minimal, because all of this is so extensible, we can just implement fancy neural network modules as separate libraries. And in fact, you'll even see that Metal and CUDA, the two main backends right now, aren't even part of the core. They are in separate crates. So if you go to crates here, you have Luminal CUDA and Luminal Metal. So the core of Luminal here, this source folder, has no idea about Metal or GPUs or anything. And a consequence of that is that it ends up being very small. So, if we check the actual line count, okay, so we have about 8,000 lines. I imagine about 2 or 3 of those 1,000 are just tests. So I would say around like 5,000 of proper code. And we want to always keep it very small. But yeah, so then the goal for the next edition is the next version is that we achieve near SOTA or SOTA performance on the M series Macs and near SOTA on CUDA for inference. I also want to do training. I want to enable training through an AutoGrad compiler, so that will also come soon. And yeah, eventually implement distributed training, and then of course build the Dyson swarm. So that's where we're going. If you're interested at all, I'm going to do some follow-up videos that'll dive deeper into specific concepts, specific compilers that have been built, and specific decisions that have been made. But yeah, this was just like a very high-level, quick overview of the library and a quick demo on how to use it. If you're interested, of course, check out the Mistral example. I would say is the best place to look if you really want to understand how to run like non-trivial networks here. And of course, submit any issues you have if you have any questions, and we have a Discord server, so feel free to hop on that. And yeah, thanks for watching.